So guys, this is where we're at. This is where we're going. So the question that we began to answer last time was, where on earth do these numbers come from? How do we know how much energy is lost or gained when reactions take place? And last time in class, we sort of fleshed out the left-hand side of this. And we said, well, we can come up with these numbers empirically. We do that through a laboratory process called calorimetry. We talk specifically about coffee cup calorimeters, and we talked about how coffee cup calorimeters allow us to take the energies of aqueous reactions, dump that energy into water, and by knowing how much energy the water changed, or I'm sorry, how much energy the water gained through temperature change, then we can figure out how much energy the reaction lost, and we can use that to figure out delta H. You get the idea? Now we're going to do this through a process called Hess's Law. Now guys, I'll define Hess's Law for you in just a moment. But what you need to understand is that Hess's Law can be approached, for lack of a better term. Hess's Law can be approached both computationally and it can be approached via manipulation. Now, sorry, it's a little play on words. The AP authors will manipulate you, because you understand what manipulate means, right? By working on something and forcing it to do something. Well, guys, the AP authors will manipulate you. When you see a Hess's Law problem on the test, based on the data that they give you, you will either have to answer it through manipulation or through computation. And I'll teach you how to identify which way they're manipulating you into using, and it'll make more sense as you understand the differences. But guys, in order to understand this, the first thing that you've got to understand is Hess's Law. So guys, let's talk Hess's Law first. Ready? So starting here, Hess's Law, and this is where you're going to pick up your notes. Guys okay? Okay, so guys, I don't think you need to write this down, but let me give you Hess's Law in a nutshell. You ready? Again, don't write this down. Actually, I'll put it on another slide so you don't even think you should write it down. So, here's the idea. This is north, okay? Here's Orem, here's Salt Lake, here's Ogden, okay? Now, say that I need to take a trip to Salt Lake, but I've got to drop something off in Ogden first, okay? So, again, this is Orem, this is Salt Lake, and this is Ogden. So, and I-15 obviously connects them. So say that I start in Orem, and I set my odometer, and I drive 90 miles to Ogden, and I drop off what I need to drop off, and then I drive back to Salt Lake, and I drive another 40 miles. How far is it from Orem to Salt Lake? 50 miles. See, guys, we understand the idea that if we can take a journey and if we can break it into steps, regardless of the direction of those steps, when we add the steps together, they give us the magnitude of the entire journey. Now, guys, imagine if we did this. Imagine if now we went from Orem to Salt Lake to Ogden to Tremonton. And so we now understand that this is 50, and we understand that this is 40, and this is 20. How far is it to Tremonton? 110. You get the idea there as well, right? So guys, what kind of math are we actually doing as we make these calculations? Well, here we can clearly see that we're adding, right? Well, guess what? We're actually adding here as well. But we're adding negative numbers because these have got direction. So guys, the idea is that in order to figure out this distance, the distance from Orem to Salt Lake, what we've actually done is taken 90 and added negative 40. See what I'm saying? You may be thinking that you're subtracting, but you've got to get comfortable with the idea that what you're actually doing is adding negative numbers. The reason this is important is because this is what Hess's Law is all about. Don't write this down yet, but guys, functionally, this is Hess's Law. Hess's Law tells us that if we can take a journey and break it into steps, and if we know the distance of each of those steps, we know the distance of the whole journey. Now guys, what if one of the steps in that journey is going the other direction? Then it's negative. So guys, what does this have to do with chemistry and energy? Well guys, the journey that we're going to talk about is the energy that's involved in a reaction. Does that make sense? But what are the individual steps? Where those are the forming and breaking of bonds that lead to the energy of the overall reaction. Now guys, you got to understand this, and if you don't, you might want to write it down. When we break bonds, does energy go in or come out? Every single time, in or out. When bonds break, energy goes in. Guys, think about, okay, so give me a pen. If I want to take the cap off the pen, what do I got to do? Add energy to break them apart. Or maybe I could show it to you this way. Snatoms. So guys, if I have a water molecule, and if I want to break this water molecule apart, I've got to add energy and break them apart. So guys, any time a bond breaks, energy goes in. Now what happens when bonds form? Energy comes out. Sounds like you didn't know that, so we'd better write that down. So guys, in your notes right now, underneath Hess's Law, add that. Breaking bonds, energy in. Forming bonds, energy out. Breaking bonds, energy in. Forming bonds, energy out. Every stinking time. Just like if I want to take Isabel's pen and break it apart, I got to add energy to it. But unlike Isabel's pen, the lid will snap back on without any energy going in. We see that better here. In order to get the hydrogen away from the oxygen, I've got to break the attraction. That takes energy. But this attraction spontaneously forms and energy goes out, in this case the form of sound, but that's not really what happens in bonds. But guys, the idea is energy in to break, energy out on formation. Does that make sense? Now let's add some terms to it. If energy has to go in to break bonds, what type of process is that? Endothermic. What about when energy goes out when bonds are formed? Exothermic. Include that in your notes as well. So guys, when energy goes in, bonds break. When energy comes out, bonds form. So now guys, let's do this relative to Hess's Law. Ready? This one you might want to write down. Methane, oxygen, carbon dioxide, water. It's not even balanced. Let's not worry about it. So guys, what is methane? Not a carbohydrate. There's no oxygen. What is methane? It's a gas. It's a hydrocarbon. Where do we find it? In here. Guys, natural gas, the stuff that you burn in your furnace at home, the stuff that we burn in Bunsen burners is primarily methane. There's a little bit of ethane and some other trace gases in there. And then they put an odorizer in it. Did you guys know that? That natural gas actually is odorless. The problem is if you leave your stove on and you're filling your house, if it doesn't light and you're filling your house with methane, you flip the light switch, you get a spark and your house blows up. You would never know it's happening because methane and natural gas are odorless. So that smell that you smell is actually not the natural gas. They put an odorizer in there so that you can smell it so you don't blow yourself up. So, guys, that's methane, oxygen, carbon dioxide, and water. What kind of reaction is this? Combustion reaction. Okay, so guys, I'm a little out of space, so I'll write it down here. What's delta H for this process? Positive or negative? Negative. Why? Because how do we know? Because energy comes out. It's exothermic. That's what heats our house. But now, guys, ready for this? Why? Why is burning methane an exothermic process? Go ahead.
Because you break up the bonds of the C and the H1.
Okay. Okay. Think about it this way. What has to happen in order for this stuff to turn into that stuff? They got to break apart. Guys, this has got to turn into carbon, hydrogen, hydrogen, hydrogen. This has got to turn into oxygen, oxygen. They've got to break apart. And when they do, is that endo or exothermic, given what you just learned? Endothermic. That's a positive process. Energy goes in to break the bonds. Now that they're all busted apart, now they can reorganize and you can get the well, it's not balanced, so it's not going to work out quite right. But guys, then they can bond together and they can form carbon dioxide and water. And now when they bond together to make the products, is that endo or exothermic? That is exothermic. So guys, now, why is the overall process exothermic? And the answer is this. Because the energy given off when carbon dioxide and water form is greater than the energy taken in when the methane and the oxygen break apart. Do you get it? So now let's tie this back to Hess's Law. Hess's Law says if you know the distance from Orem to Salt Lake and the distance from Salt Lake to Ogden and the distance from Ogden to Tremont, and how do you figure out the whole distance? Add them up. Well, guys, the same thing applies here. How do we find out the total amount of energy that's lost? We need to know the amount of energy that's gained, and we need to know the amount of energy that's lost, and then we add them together. And because the lost is bigger than the gain, the overall amount of energy is negative, and that makes the reaction exothermic. Guys, that's the idea behind Hess's Law. And so the idea is this. If we know the amount of energy that it takes to break this apart, and if we know the amount of energy that it takes to break this apart, and if we know the amount of energy that's released when this forms, and we know the amount of energy that's released when this forms, and if we add all four of those together, guess what we get? The overall energy of the reaction. Does that make sense? Okay. So guys, if you understand that, let's put a sharper point on Hess's Law, and then let's talk about how we can apply this idea and do some calculating. So guys, it goes like this. This is Hess's Law in word form. It sounds better if we do it this way. If a reaction can be broken down into a series of steps, the sum of the enthalpy changes associated with these steps will equal the enthalpy change of the complete reaction. Was that pretty good? Ooh. Please keep hands and feet in the ride at all times. Yeah. Yeah.
You gotta say it like 10 times faster.
I can't. That's right. So guys, this is the deal. If you can take a reaction and break it down into a bunch of steps, And if you know the energies of the steps, then you can figure out the energies of the whole thing. That makes sense, right? It makes sense going to Tremonton. It makes sense going from Ogden back to Salt Lake. We just make one of them negative, kind of like endo and exothermic. And if we can add up the steps, we can make this all work. You get the idea? You understand the concept? You're still writing. I think we should consider a field trip. I would love to take you guys to BYU and plop you in the middle of a session of Chem 105. I don't know. I think it would be fun if we could. It would be great to allow you guys that opportunity to experience what this looks like in college. You'd learn to take notes a lot faster. Oh yeah, oh yeah. You don't even have time to write words. You're just chicken scratching. So guys, please don't write this down, even though I know you're going to anyway, but I'm not going to give you time. So guys, these enthalpy changes, these processes can be approached two different ways: through manipulation and through computation using what are called heats of formation. So guys, here's what we're going to do. We're going to do this one first. Whoa, that's a bad color. We're going to do this one second. We're going to do heats of formation first. This is actually out of order in the notes, but the way our conversation for Hess's Law has gone, it's going to make a lot more sense. So if you're following in the notes, you're going to have to try to find where we are. You guys okay? Okay, so here's what we've said. What we've said is this. Hess's Law is all about breaking big things into little steps. And if you know the magnitude of the little steps, you add them all up and you get the energy of the big thing. You're good on that? Okay. Then we talked about this relative to the combustion of methane. And we talked about the little steps. What are the little steps? What color are the little steps in? Green. So the little steps go like this. How much energy does it take to break up CH4? How much energy does it take to break up O2? How much energy does it take to form, notice the word, how much energy does it take to form CO2? And how much energy does it take to form H2O? Do you understand where we're going with this? Because if we know those numbers, how much energy to break, how much energy to break, how much energy to form, and how much energy to form, if we know those numbers, how can we find the energy of the whole thing? Add them up. Does that make sense? Okay, now let's do this. What do you know the value will be? What do you know the value will be for the amount of energy that is released when these form? Will it be positive or negative? Negative, because that's exothermic, because bonds are forming. Now, what do you know the values will be for these as we break these apart? Positive, because energy is going in. Does that make sense? Now the question is this. What do we call these values? What do we call the numbers that represent the energy to bust these apart and the energy to put these together? And the answer is this. These are what are called, I'm so sick of that color. Guys, these are what are called, and this is going to be the next thing in your notes, so you may as well write it down in your notes. These are what are called heats of formation. And that's what we've got to talk about now. So guys, this is our transitional thought. If we want to know the energy of the whole reaction, we need to know the energy of the steps. And the steps that we're talking about is breaking these apart and making these. And the amount of energy that it takes to do that for each one of these is what we call the heat of formation. Now, guys, let's have a little side conversation. That makes sense, right? This would be the heat of formation to make this, and this would be the heat of formation to make this, right? But wait, why doesn't it make sense to talk about the heats of formation for these? They're being broken apart. But guess what? The heat of formation is still useful to us in this. Because guess what? The amount of energy that's released when these are formed is equal to the amount of energy that it takes to break them apart. So if we know the heat of formation for methane and oxygen, how do we turn that into a heat of decomposition to break it apart? Change the sign. Does that make sense? Let's do this. So this is the idea. If we know the heats of formation for these, that's great, because those are being formed. If we know the heats of formation for these, that's still great, even though they're not being formed. Because they're not being formed, they're being destroyed. But the amount of energy lost when they're formed is equal to the amount of energy that has to go in to destroy them. So we just change the sign, and now these numbers help us as well. Does that make sense? Okay, so guys, let's now talk about more formally about heats of formation. So guys, it goes like this. Let's go here, and I need to find the slide that we're on. I don't have a number. Okay, hold on. Let me go back. I'm just going to find it. Not that, not that, not that. I think this is it. Yeah, there we go. Okay. So guys, remember when I told you the other day that heats of formation, that enthalpy and heat we're going to use interchangeably because we've already gotten rid of work? Here's an example of this. Technically, these are what are called enthalpies of formation. Heats of formation is just fine. Here's what you need to know. Enthalpies of formation, we'll also call them heats of formation. By definition, it's this. By definition, it is the change in energy for the formation of 1 mole of a compound from its component elements. Doesn't that make sense? That's why we call them formations. How much energy is needed to make a mole of a substance from its component elements? Guys, it's abbreviated like this. Delta H naught sub F. And we'll talk in a second. Guys, just write it down. Look at it, write it down, we'll talk about it. So it's delta H naught sub F. And guys, the naught is the little degree symbol, but that is not a degree symbol. It's read naught. K-N-O-T, naught. And guys, what does it mean? Well, guys, and this is true for the rest of the year. You're going to see this all the time. The naught means at standard conditions. So what are standard conditions? The naught symbol means standard conditions, which are generally 25 degrees Celsius and 1 atmosphere of pressure. But guys, just practically, you're not going to see examples where things aren't at standard conditions. So all this functionally means is you know what values to use because you can look them up. So where do we get these values? Well, grab your books. Open up, guys, to page 184. When you look with me at table 5.3 on page 184, you will see a standard enthalpy of formation table. You got it? So guys, allow your eye to scan through that table. And what do you notice about the values? Most of them are what? Negative, right? Why? What does that mean?
It's forming bonds.
Right. So when these things form, as we said, right? When these things form, energy is given off, and that value being negative tells you the energy is being given off, and it tells you how much energy is being given off. Does that make sense? Okay, hold on. So now, guys, go to the very bottom right-hand corner of this table, and let's really talk about what this means. So let's look at water, and specifically water vapor. We picked this because everyone can go bottom right. We can do this for any of them. So what does that number, negative 241.8, mean? Well, guys, it means this, that if you take 2 moles of hydrogen and 1 mole of oxygen and you bond them together, and it makes no, that's not true. So we're going to make water. And water is made from hydrogen and oxygen. So if you take 1 mole of hydrogen and if you take half a mole of oxygen and react that together to make a mole of water in its gaseous form, that will release 241.8 kilojoules of energy. That's what these values mean. So again, the idea is it is the amount of energy when a mole of a substance is made from its component elements. Do you get the idea? And so, guys, you can go through and you can now understand that each one of these values actually represents a synthesis reaction. Think about that. Each one of these values represents a synthesis reaction where the atoms are bonding together to make the compound. So if you go top right, let's look at HCl. Well, what does that mean? Well, to make HCl, we need half a mole of H2 and half a mole of Cl2. And when that bonds together, it makes 1 mole of HCl and 92.3 kilojoules of energy comes out. Do you see how this all fits together? So now I have a question for you. Why aren't they all negative? We're going to talk about it in the next chapter. Why aren't they all negative? We can't answer that yet, but we will. But guys, the other thing that I would ask you is this, and I don't think you'd ever notice this, so let me just tell you. And understand this isn't an exhaustive list, right? You could do this for every compound on the planet. But the thing that I need to point out to you is this. The diatomic molecules are not on here. Hydrogen, H2, O2, Cl2, Br2, I2, N2, O2, those guys, right? None of the diatomics are on here, and there's a reason. They're all understood to be 0. You need to write that down. Let me put it up on the screen. Guys, all the diatomic elements are assumed to have a delta H, a heat of formation of 0. You get the idea? You okay? Okay, so now, guys, we're going to have some fun with this. Y'all caught up with me? Keep your books open. I think I've got to do this and this. Okay, so here's what we're going to do. Now, given everything that we understand, we're going to figure out the energy for the combustion of methane. But I'm going to start with the clean screen because this is a train wreck. Okay? So guys, do this with me in your notes. Here we go. So we're going to go CH4 plus O2 yields CO2 and H2O. Yes. Now we've got to balance it or the math doesn't work. So 1 carbon, 4 hydrogens, 2 hydrogens. So we need a 2 and we need a 2. Okay? Now guys, let's do this. In order to figure out the whole journey from here to Ogden to Salt Lake, what we need to know is the energy that is involved in each one of these processes. So what processes are we talking about? Well, we're talking about making these and breaking these, right? So let's do the making first. How much energy is involved in the production of 1 mole of carbon dioxide? I pray it's on here. Oh, beautiful. Carbon dioxide, how much energy? Negative 393.5 kilojoules. Let's write that down. Negative 393.5 kilojoules. I'll write the kilojoules too. So now, guys, how much energy is involved in the formation of the water? Well, it does depend. So let's say this is exothermic, right? It's hot. When you light your Bunsen burner, it doesn't rain. It's not making liquid water, it's evaporating into gas. So let's use the water vapor number. Negative 241.8 kilojoules. Oh, golly. Yes. Negative 241.8 kilojoules times 2. Now, guys, let's go. From Ogden to Salt Lake, we now need to know how much energy is involved with our reactants. But this isn't energy coming out. This is going to be energy going in because they're breaking down. So now we got to find methane. And we find methane and the good. Guys, look at the number. Negative 74.8. But what does that number represent? The amount of energy that forms methane. But methane ain't forming, methane's busting, so what's the number? Positive 74.8. And guys, the positive is understood to be there. You good? Okay, now, how much energy does it take to break apart the oxygen? None. This value is understood to be 0. So now, guys, how do we find the energy of the overall process? We add it together. So we go 74.8. We subtract from that 393.5. And we subtract from that 2 times 241.8. And I get negative 802. Can you confirm or refute? Is that right? Yes? Okay. So guys, the overall value then is negative 802.3 kilojoules. Yes. And that's the point. Guys, the way that we would represent this in chemistry land would be delta H is equal to negative 802.3 kilojoules as written. What do you think? You okay? Do you see how this relates? Now, guys, check this out, because this is about to become easier. Look at what we did. Don't miss this transition, because this is going to be pretty cool. Guys, look at what we did. What are each of the numbers that I underlined? What are those? Right there. Standard enthalpies of formation. So let's try this again. What are those numbers? They're heats of formation. We call them standard enthalpies of formation. But in the real world, if you were in a chemistry department at a university, you would just call them heats of formation. That's fine. So, guys, those are the standard enthalpies of formation or the heats of formation. And of course, you have to memorize these. No, they'll be given to you on the test. But guys, these are what are called heats of formation. Now look at what we had to do with them, and don't miss this. Look at what we had to do with them in order to make them into something that allowed us to come up with this number. What did we have to do? Well, first of all, what did we have to do to the numbers on the left-hand side? Change the sign. Why did we have to change the sign for those numbers? Exactly. They're not forming. They're breaking. They're reactants. By definition, they're not forming. They're breaking. And so consequently, we had to change the sign to respect the fact that if these are formations, them ain't forming. Then, guys, look at what else we had to do. What else did we have to do? Multiply by the number of moles. Yes? So let me summarize for you mentally. In order to make this math work, what do we have to do with these heats of formation? One, we have to change the sign of the reactants. And don't write this down. What do we have to do? One, we have to change the sign of the reactants because they're not forming, they're breaking. And two, what do we have to do? Multiply by the number of moles. Guys, check this out. Write this down with me. You ready? Write this down with me. Hold on. Do you get it? Guys, let's talk. You all done writing? Let's talk. What is this? This is the enthalpy change for the reaction. You'll notice that this should be a sub F. Oh golly. Sorry, let me make it red. This should be a sub F. So guys, you'll notice over here, this is not a sub F. This is not an This is this. This is the energy of the reaction. But guys, what does this stuff mean? Well, N is number of moles. What is delta H naught sub F? What is delta H naught sub F? Look up in your notes. The heat of formation. And of course, PROD stands for products. Now guys, what does the squiggly guy mean? Add them up. Means sum. So let's do this. What does the squiggly mean thing? Add them up. What does N mean? Moles. What does delta H naught sub F mean? Heat of formation. What does RCT mean? Reactant. Guys, listen. This is the equation that describes this process. What did we do? Well, to find the energy of the reaction, we took the heats of formation for all of the players. And what did we do with the reactants? Changed the sign. Why? Why? Because the reactants are breaking apart. That's what this negative sign does. That's why we subtract the product or the reactants. We subtract the reactants because subtracting is the same as changing the sign, and we change the sign because they're not forming, they're breaking. Then guys, look at the other thing we did. We multiplied by the coefficients. Why? Because we've got to account for the number of moles. That's what this does. So what it is saying is this. If you add up the heats of formation of the products times the number of moles of each, and then if you add up the heats of formation for the reactants times the moles of each, and then if you take this and subtract this, it will give you the heat of the reaction. But guys, all that's doing is this. Do you get the idea? Now guys, look on your AP equation sheet. Find this equation. You see it there? Page 4 side? Third equation down. What's missing? The ends. They are assuming that you know to multiply by the number of moles. If you'd like to see it in the form that it is represented on the wall, look on page 186 in your book. I prefer this form better. You see it there, equation 531? You'll notice they include an N and an M. But understand it's not on the equation sheet for the AP test. So the understanding is that you'll remember. Yeah. Oh, I don't know. Did I do it wrong? Oh, sorry, the knot's in the wrong place. Okay. You guys okay? Okay. So guys, we have now done this. We have now talked about, just a moment. Oh, where am I at? Oh, there we go. We have now talked about this. We have talked about how to do these through computation using heats of formation. Now we've got to talk about how to do this through manipulation. So let's do that to wrap up the day. So we're done with Hess's Law. Let me go down another slide just a second. Okay. Hess's Law by manipulation. So guys, Hess's Law by computation is the equation we just put up on the board. But here's the thing they're going to do to you. Sometimes they will not give you a heats of formation table. They will ask you, what is the overall and what is the heat of reaction? But they won't give you a heat of formation table. They'll give you some different data. And when they present the problem to you like this, they're asking you to solve, to find the same answer, the heat of reaction, but to solve for it not through that what we just learned where you take products minus reactants. They're asking you to solve it through a process called manipulation. The problem might read something like this. Write it down with me. It says calculate the enthalpy of combustion when carbon becomes carbon monoxide. And then guys, they're going to throw something like this at you. I'm just going to give it to you, let you write it down, and then we'll play. They'll give you data that looks like this. Just write it down and then we'll talk. You guys all caught up? You okay? How about now? You okay? So guys, let me ask you a question. If you were presented something like this on the AP test, how would you know that you can't do this? How would you know you can't solve this question using the equation that we just saw that says products minus reactants? Here's how you know. This equation is a heat of formation. Do you see why? The element carbon, the element oxygen forming the compound carbon dioxide. Guys, that is a heat of formation by definition. Remember, heat of formation is the amount of energy needed to create 1 mole of a compound from its component elements. That is a heat of formation. Why is this not a heat of formation?
So you need to break carbon monoxide.
Carbon monoxide is not an element. Guys, carbon monoxide is a compound. Consequently, this is not a heat of formation because that's not an element. So the question then becomes this. What can we do to figure out the answer to the question if we can't go squiggly guy N delta H naught products minus reactants? Well, guys, the answer is this. We need to manipulate this thing. And this is the way we do it. Ready? The first thing we need is a target. We need what we call a target reaction. It's what we're solving for. So the question says this. Calculate the enthalpy of combustion of carbon to carbon monoxide. So guys, what does that reaction look like? Let's write it down together. What does that reaction look like, carbon going to carbon monoxide? If you've written this down, skip down 3 lines and write this down with me. It looks like this. Carbon plus something, carbon plus something turning into carbon monoxide. So guys, what is that something that we're missing to turn carbon into carbon monoxide? Oxygen. But oxygen doesn't hang out by itself. It's O2. Exactly. We need half a mole of that. Now we've got what we call our target equation. Some people call it a subject equation. Now what we need to do is we've got to figure out what we can do to these guys to make them look like this guy. And we do that through a process called manipulation. So guys, this is how to play the game, ready? And this is what they'll give you. They'll give you some equations, and then they'll give you either a subject-target equation, or they'll give you a statement that you've got to write the equation for. If they do that to you, typically part A will be write the equation. Then part B will be figure out the energy. But it goes like this. In order to do this, what we're going to do is we're going to take these equations and mess with them to make it look like this equation. And here's how you do it. You look at, you look at the first component of the reaction, of one of your given reactions, and it's carbon. And we've got carbon here, and what you look for is 2 things. Placement and number. So here's the idea. We've got 1 carbon there, and it's on the left. Now guys, where's our carbon down here on our subject reaction? On the left, and do we have the right number? 1 carbon, 1 carbon. That means that this reaction's done. We don't have to mess with it. So now guys, we do this. We look at our next reaction. And we go, okay, our first component is carbon monoxide, and we go and find it in our target reaction. What do you now notice? It's on the wrong side. Are the numbers correct? 1 and 1. So the numbers are correct. The problem is it's on the wrong side. So guys, what do we have to do? We've got to flip this reaction over. So we are going to rewrite this. CO2 yields CO plus 1/2 O2. Do you see what I did? I just flipped the reaction over. But guys, when I flip the reaction over, what else do I have to do? Change the sign. So now I've manipulated that guy. This is now gone. Now that I've manipulated all of my equations, it's now time to bring them together. And guys, here's what you do. Draw a line underneath this. And then what you're going to do is bring everything down. So go to your first equation and bring down the reactants. C plus O2. Now go to your second equation, bring down the reactant, CO2. Notice that we're looking at the equation we manipulated. Now guys, let's look for our products. Our product in the top reaction is CO2. What are the products in our bottom reaction? CO and 1/2 O2. Now guys, what do? We cancel stuff out. We've got a CO2 here and a CO2 there, so those cancel. Will anything else cancel? 1/2 of an O2. If we get rid of 1/2 of an O2 there, what's left over here? 1/2 of an O2. You get it? This is now the same as this. See it? We've got a C, we've got 1/2 of an O2, and we've got a CO. So we just made these reactions add up to this reaction. Now what does Hess's law say? If the reactions add up, guess what else adds up? The numbers. So if we take the energy of this reaction and the energy of this reaction and add them together, it will give us the energy of our target reaction. So we go negative 393.5 and we add 283, and we now know that the delta H for this reaction is negative 110.5 kilojoules. That is the process through manipulation. You'll see both.